Okay, sorry, I'm staring at the screen again. Let's look at some of the feedbacks in the system, and this terminology we have used already many times. I think you know what it is. So let me quickly explain what a positive feedback and negative feedbacks are. I think you already intuitively know it. A good example of a negative feedback system is the thermostat, right? So let's say you have a heater on or an air conditioning on, which has got a thermostat, so it is measuring temperature, and if the temperature falls below the set value, it will turn on the heat in a cold condition, or it will turn on the AC if it's above a certain threshold, and when it reaches the temperature you want, then it stops or right. So it is a system that maintains temperature that you want to set. That is a stable system, and it is got a net negative feedback, right? Whereas you have positive systems, positive feedback systems, where the things get amplified, and we mentioned CO2 in water, for example. So if CO2 increases temperature of the atmosphere holds more moisture, water vapor is a greenhouse gas, so that further increases the temperature, and that further increases the water vapor, and so on. So those are positive feedbacks, and there is usually a limit which decides how far this feedback can keep going. For example, on Venus, the runaway warming has resulted in a surface temperature of 460 degrees centigrade, right? So these are the examples. Also, Mars has cooled to minus 50 degrees centigrade. So here are the examples from the real world. We are looking at a situation where we have, again, top of the atmosphere with solar radiation coming in and infrared going out, and we have a glacier being shown here where there is a surface mass balance and elevation. So there is a albedo feedback, so sun's energy coming in is going to be reflected by a lot, because the albedo of glacier and snow is high, which means that tends to reduce the amount of energy in the system and lead to further cooling and lead to further surface mass balance and elevation increase. Okay, so on the other hand, if there is water below, you can have warming that can create melting from below and reduce the ice mass and so on. So it can create marine ice sheet instability, which is considered a positive feedback, which I will not get into here. But typically when land glaciers flow down the hill onto the ocean, they extend into the ocean like this, away from the grounding line, because ice floats, and that creates ice shelf, which typically, because of the wave activity and because of the warming from the waters, they tend to be unstable as well. Clouds, so cloud optical depth, the thickness of the cloud, it can be positive or negative depending on whether it is able to reflect enough sunlight, and how much it's going to allow, and how much of the outgoing heat or infrared radiation it is going to absorb. And of course, anything that absorbs heat and gets warmer is going to also send energy back towards the surface. So whether it's a net positive or net negative depends on many factors, and in fact it's one of the big unknowns under global warming, whether clouds will act as a net positive or a net negative. Okay, so ice growth thickness can be a negative feedback, because once the ice grows, it insulates the ocean from exchanging heat with the atmosphere, and it has high albedo, so it can then grow thicker. But depending on whether it's sea ice or shelf ice, again, we haven't talked about this, it can become a very different process. So here ice shelf melting is being talked about. So this is part of the glacier, which means it's just mostly fresh water that's frozen and is going to disappear based on whether it has a positive feedback or negative feedback. So ice production and entrainment, here you can have feedbacks below, where if the cooling is going to freeze more water and keep the volume of the shelf ice then or sea ice, you can have different reactions. It's complicated because if you're freezing ocean water to produce sea ice, then you're going to release the salts from the water, from the ice. It's called brine rejection, and then some other circulation gets set up, so I don't want to get into those kinds of details here. So there are also cloud ices which can have positive feedback. So the Arctic polar amplification that we mentioned before probably has some water vapor and cloud ice, sea ice cloud feedbacks that are positive as well. Ocean heat transport and circulation are a big part of the overall feedbacks, and we will see that there are various time scales involved here. Of course, we have the Planck feedback, where if we have global warming, we will increase water vapor, we'll increase atmospheric temperature, and by sigma T to the fourth, we are going to increase the amount of energy that's going out. We will visit the lapse rate in a minute. There is also atmospheric heat transport and circulation changes related to global warming and so on. Lapse rate is basically the gradient of temperature in the vertical. So we are here looking at over a ice flow. So it's cooler near the surface than above, but typically you will have warm surface and decreasing temperature, and the question is whether lapse rate will decrease or increase with global warming, which we will see in a minute. Okay, so what are the time scales? So here are some time scales. Snow, ice, albedo. So things are going here from hours to days to years to centuries. And ice albedo feedbacks, they are a positive feedback. So if ice starts melting, albedo decreases, more energy is absorbed, it gets warmer, more ice is melted. Whereas if glacier is growing, albedo increases, it gets colder, glacier will glow further. But we saw that there is an asymmetry in this ice albedo feedback because growth of glacier is slower and slower. Methane from peat and permafrost decomposition is a positive feedback, because as peat and permafrost decompose and release methane, methane is a very strong greenhouse gas. It's going to increase the warming and further drive the thawing of permafrost and peat. Okay, long wave radiation, you expect that warming is going to increase long wave radiation, so that's going to be a negative feedback. Lapse rate, we will see, can be positive or negative depending on what actually happens. Ocean circulation can also be positive and negative depending on whether the ocean is able to take the heat down and take it away from the atmosphere, or it's going to release it somewhere else. And there are positive and negative feedbacks with the clouds that we just mentioned. Water vapor we already mentioned. Emission of non-CO2 greenhouse gases. Black carbon is a positive feedback because it absorbs radiation and warms the climate, whereas sulfur dioxide dissolves in water, produces sulfuric acid, which actually scatters light and has a cooling effect. So they kind of go together and often tend to cancel each other. Okay, so air-land CO2 exchange and biogeochemical processes depends on whether vegetation grows more and takes up more CO2, or vegetation begins to die and release more CO2. Same thing with soil, whether soil continues to keep carbon, or warming leads to higher respiration and release of carbon dioxide from the soil. Rock formation and weathering, they are very slow time scale processes, but with warmer temperatures and more humidity, more CO2, you're going to have more carbonic acid, which is going to drive higher weathering rates, which draws down CO2 and puts it into the ocean. And there are other biogeochemical processes, and it's the exchange of CO2 itself. So as CO2 in the atmosphere increases, ocean is either going to put out less CO2 because the gradient of CO2 is reduced, or there are places where more CO2 can go into the ocean. So look at the time scales here. Long wave radiation is in hours to days. Lapse rate also is in hours to days. Water vapor typically is in days to months. Clouds are days to months as well. Snow, ice, albedo will be in days to years. Negative changes to positive changes in this century. Air-land CO2 exchange is in this range of centuries by geophysics. Non-CO2 greenhouse gases and aerosols, air-sea CO2 exchanges, peat and permafrost, land ice, ocean circulation, all these are slow timescale feedbacks. So the system, how fast it is warming in the atmosphere, is going to be determined by how glaciers are behaving, how ocean is taking up carbon dioxide and heat, how other changes in permafrost, land ice, and air-sea CO2 exchange are happening, and ocean circulation itself is changing over this time as well. So here is a quick example. So here is the radiative forcing that we talked about and how temperature is changing. So you have emitted terrestrial radiation with Planck feedback. So if temperature increases, that's going to increase the emitted terrestrial radiation because surface temperature goes up. So it will be a negative feedback. Water vapor is a positive feedback. Lapse rate here is shown as a negative feedback. We'll see that in a minute. As we said, lapse rate is this gradient in temperature, right? So we're going from the surface to the tropopause, and with global warming, the surface is expected to warm more, and condensation heating is going to happen because moisture is increasing and so on. So the upper atmospheric temperature also will change. So whether the lapse rate increases or decreases and how the stability changes determines rainfall and other processes. So this lapse rate here is shown as negative. Snow, ice, albedo feedback. If temperature warms, it's going to melt these, and that's going to increase, decrease albedo and increase radiation absorbed. So it's going to be a positive feedback on this side. Clouds, it's unclear. Okay. So here we are. Temperature of the atmosphere. Temperature of the atmosphere plus the Planck feedback, water vapor feedback. So this is in the near the tropopause. This is at the surface. So you can see that they're not equal at all. So you have long wave radiation. You cannot even read this. Water vapor feedback and cloud feedback, and the snow and ice albedo feedback. So just get a sense how difficult this is going to get when we look at the whole system. Lots of feedbacks are happening at lots of different time scales. So the net warming is going to be critically depending on the time scales of these feedbacks and which is a dominant feedback. So going back to our Clausius-Clapeyron, if you remember, as temperature warms, there is an exponential increase in water vapor, which is a positive feedback, and that's going to affect the lapse rate as well. So here we are looking, if there is no lapse rate feedback, then warming is going to just shift the entire profile to be warmer at the surface and in the upper atmosphere. So the radiative forcing is going to shift it. If the warming is less near the surface and more above, then larger temperature changes will happen in the upper troposphere. It will be a negative lapse rate feedback, so global warming will be damped by lapse rate changes, whereas if it is a positive feedback, then larger temperature changes will happen near the surface and smaller changes will happen in the upper atmosphere. Why is this negative feedback and why is this a positive feedback? We will see that later on, because you will have to understand how the outgoing long wave radiation is going to change. In a simplistic sense, you can think that if temperature is warming less here and more here, more long wave radiation is coming in, less is going out, because sigma t to the fourth is going to be smaller here than here. So on the other hand, here sigma t to the fourth is larger here than here. So this is sending more energy to space than this one. So this will reduce the warming, and this will increase the warming. Okay, those are the kind of things we have to worry about. Let me leave this here and come to climate sensitivity in the next podcast, because this one is already 15 minutes. But I think you are getting a sense. We are just adding a little bit of difficulty, complications, complexities with each step. But this chapter is critical in terms of understanding the theories that we need to understand climate science, especially climate change. Okay? All right.